Now, are you able to see my screen?
No, sir, no.
Just wait. मीटिंग चालू है ना 4:30 5:30 क्या लगे नहीं मुझे कुछ करना है और है इनके को ना सर ऑटोमेटिक हो सब अभी तो नहीं तुम्हारा वो बोला नहीं ना ये लास्ट टाइम ऑटोमेटिक से मुझे चाहिए ना हम तो सब आया ऑटोमेटिक मूव पूरा से एक्टिवेट है जब तो देखो ऐसा देखिए पर आपको लैपटॉप मूव की ना ସେଇଆ ହଉଛି ଆଉ ସେଇଥିପାଇଁ ଆପଣ ମୁଁ ତ ସେଗୁଡା କିଛି କରୁନି ସେ ମୋର ପୁରା ଗାଡି ରହିଗଲା ସେଗୁଡା ଆସୁନି ତାହେଲେ ମତେ ଆସୁନି ସେଇଟା ସବୁ କରିବା ଆପଣ କରୁଛି ଆପଣ ମୁଁ ଫୋନରେ ଖୋଲିକି କରୁଛି ଆଗ ନମ୍ବର पीपीटी टा कौन से और पीपीटी टा देखे लगी रे सेठी हां ऐसा शो करो एडमिट सब होचंती का पीपीटी टा मोड काम करू छी सब बंद कर
I can see your screen. Yes, sir, your screen is visible.
So I hope now the screen is visible.
Yes, it was visible, sir. Now your other screen has come. Earlier PowerPoint was visible. Should I try from my side?
Then
chair ऊपर नीचे ना.
Let me. So, good afternoon to all of you. I hope I am audible. So, this is the 39th Siksha and Anusandhan fortnightly academic lecture, and we have with us one of the celebrated director of Jawaharlal Planetarium and administrative head Jawaharlal Nehru Memorial Fund, Prayagraj. Just for the audience, let me tell you that this Siksha and Anusandhan fortnight academic lecture was conceived by our Vice Chancellor Professor Ashok Kumar Mahapatra, and the first SOAFAL lecture was delivered on 20th February 2021. From then, uninterruptedly, we have conducted 38 webinars of which were delivered by eminent persons, bureaucrats, ambassadors, academicians, professionals, social activists, and today this is the 39th oration of the Siksha and Anusandhan fortnightly academic lecture series, and we have amongst us Dr. Y. Ravi Kiron. Welcome you, sir, to this August gathering. Now it is my duty to introduce to the audience to today's speaker, Dr. Y. Ravi Kiron. Dr. Y. Ravi Kiron is presently the Director of Jawahar Planetarium and Administrative Head, Jawaharlal Nehru Memorial Fund, Prayagraj. Dr. Y. Ravi Kiron has a PhD in observational astronomy, especially eclipsing binaries. He is at present Director, Jawahar Planetarium, and as I have mentioned you, Administrative Head of Jawaharlal Nehru Memorial Fund, Prayagraj. He is looking after Anand Bhavan Museum, which is ancestral home of Pandit Jawaharlal Nehru. He has, to his credit, 34 years of work experience in planetarium and astronomy popularization field. His responsibilities include taking care of scientific and administrative activities, production of planetarium shows using planetarium software, and giving popular astronomy lectures to students of different levels. He has published many research papers in reputed journals. He has experience of working at many planetariums in India. We are really fortunate, and I am personally privileged to have Dr. Y. Ravi Kiron as a speaker of this distinguished lecture series. Actually, very short time, we could approach Dr. Y. Ravi Kiron, and his large heartedness can be reflected, and he was so kind in accepting our invitation in a very short notice. Of course, I contacted him through our common friend, Dr. Subhendu Patnaik of Pathani Samanta Planetarium. So now the format, as you know, sir, you will be speaking for 40 minutes, and then we will have question answer. And so you have in your audience students, then volunteers, faculties, and many outsiders also. So now I request you, Dr. Ravi Kiron ji, to kindly present today's talk, sir.
Thank you very much, Nachieketa sir. In fact, I feel honored to be part of your group for giving me an opportunity to present this talk. So the talk will be controlled by you, sir. I will be talking because the screen.
Yes, no problem. I will share. Just let me only do the
full screen or.
Yes. Now I think the screen is probably the screen is visible, isn't it, sir?
Yes, sir. First slide is there.
Yes. Then you can continue. No.
Okay, sir. Then I'll go for next slide.
Okay. Just wait, sir. Just wait.
Means if we can get the full screen, that F5 or so,
Okay,
screen.
let me go to the other slide. Why I'm not able to? It is
I think
next.
the preview of these slides are not required.
Why I'm not able to go to the next slide? Just wait. Yes. An universe, an overview. Then this is the second slide. Why I'm not going?
This is the first slide, sir.
Yes. Let me check. Sharing a window. Why I'm not able to go to the second slide? Yes.
Sir, can we get full screen little
Full screen. Yes. Okay.
F5. Yes.
Is it okay?
No, sir, but it's okay. I'll manage. In this session, what I'll talk is about the planets, all the things that we see in the universe. That is, we have solar system, we have sun, then we have stars, galaxies, nebulae, and then clusters of galaxies, and then we go into the edges of the universe. So right now we are talking about the solar system, where you see the comparative sizes of the planets. We can see here the sun is there. Sun is so big, and in front of sun how small the planets look. We can see Jupiter, and then the second planet its neighbor is Saturn, and then there are other planets, Uranus, Neptune. You can see Earth in front of sun, how small it is. In one sun, we can keep millions of Earths. That much big sun is. So this is just a comparative slide of the sizes of the planets compared to sun. Next slide, sir. Next slide, please.
Next slide. It is going. What is happening? Here it is showing, but just.
Yes, got it, sir. Oh,
Okay.
you have to click arrow with that.
Yes.
You have to. Here the distances are there. In this slide, you can see how close the inner planets are, and then as you go away from planet Mars, the planet's distance between the planets, it's too large. So Mercury, if we see in terms of astronomical units, Mercury is at 0.4 astronomical unit, then Venus is 0.7, distance between Earth and Sun is 1 astronomical unit, which is 150 million kilometers, and then the more 1.4 is Mars, 5 is Jupiter. The more far the other planets are quite farther. So the inner planets are very near to sun, and outer planets are far away. And this one, there is one orbit you can see highly inclined. That is actually the orbit of planet Pluto, which was planet at one time. Next slide, sir. Yes, I got it. So here we are talking about I'm not going to deal with all the planets because we have less time. But here we are dealing with little about the eclipses. Why we get eclipses? Mainly, we all know that solar eclipse or lunar eclipse. Solar eclipse is formed when sun comes between moon comes between Earth and sun, and lunar eclipse comes when Earth comes between moon and sun. But the point is, Earth, the sun and moon are of the same size. that is just a coincidence that the angular size of sun and moon are same in the sky. So if you see the distance between sun to earth and then the size of moon and then the distance between moon to earth, sun size, if we take the ratio, they both match. So it is 400 the ratio is, and that is why sun and moon appear to be of same size in the sky. They are known as angular size. That is why the eclipse, one object can cover the other object. Otherwise, moon is very, very small compared to sun. Next slide. So something happened. Someone else is presenting. Kaushal.
Oh, is it so? Who is presenting? Yes.
Kaushal Mishra.
सौम्या देख तू प्रतीक को डाकिल आउ के प्रेजेंट करूची कोन आउ के प्रेजेंट करूची कोन से प्रतीक कोड गला डाक टिके जस्ट वेट सर जस्ट वेट
Yes.
के कौशल मित्र बोले के उडे प्रेजेंट करूची
in the presentation it will become all right.
Yes, got it, sir. So in this slide, there is one more thing, that why do we suppose if sun and moon sizes are same in the sky, why is it that we do not get eclipses on every full moon day and new moon day? The reason is, you all may be knowing this, moon's orbit is 5 degrees inclined to the orbit of Earth. So that is why only when moon and sun are at the points where they cut each other, the orbits cut each other, then only the eclipses take place. So here you can see the favorable conditions for eclipse to happen and unfavorable conditions where the shadow falls somewhere else. Next slide, sir. Next slide.
Just wait sir just wait
Yes.
why it is not going.
Yes, sir. Here, see, recently planet Pluto is removed from the solar system. It is no longer a planet. So a new definition to planets is given. What is a planet? So according to International Astronomical Union, a planet is a celestial body. First of all, it orbits the sun. And then second thing, it has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, that is, it is spherical in shape, and then it has cleared its neighborhood around its orbit. That is more important. Like in case of Pluto, it has not cleared its neighborhood. There is a satellite Charon which is very close to Pluto, which is orbiting around Pluto. So by definition of planet, we have removed the planet Pluto. A new definition is given. Earlier it was like whatever goes around the sun is a planet. Now that definition is changed. Next slide.
Okay sir just wait.
Yes. So First we have Sun, next to Sun is Mercury, Venus. Mercury is a very hot planet. It is close to Sun, being close to Sun, the temperature is around 400 degrees, and during the night side of Mercury, the temperature goes to minus 183 degrees. And then we have Venus. Venus is the hottest planet in the solar system. The temperature is around 450 degrees. That is because of the greenhouse effect. Venus has got atmosphere of carbon dioxide. Whatever radiation falls on Venus, that is absorbed and re-emitted in the form of infrared radiation, which is again absorbed by the clouds, and so Venus is the hottest planet. Mercury is the nearest planet, but Venus is hottest planet. This is an artistic view of one lander on planet Mars. Mars is a very well studied planet, being very close to us, and also its features are very similar to Earth's features, like it has got an inclination of 24 degrees, because of which seasons are caused. So during very early times, it was thought that Mars also had rivers, dry canals, all these things. But now, with the studies of spacecrafts and the robotic machines that have landed on Mars, it is well known that Mars is a very dry terrain it has got, and Mars has atmosphere of carbon dioxide, and humans cannot sustain there. The temperature on Mars also is during peak winter near the equator, it reaches around 0 degrees. So the temperatures are not during summer, peak summer, the near equator temperature reaches around 0 degrees. That means Mars is always below 0 in temperatures. Next slide, sir. Jupiter. Jupiter is the biggest planet in the solar system. It is so big that we can keep 1300 Jupiters in 1300 Earths in one Jupiter. Jupiter rotates very fast on its axis. It takes only 9 hours 55 minutes to go rotate on its axis, going around its axis. And Jupiter is it's made up of Jupiter, Saturn, Uranus, Neptune, all these 4 gaseous chains. They are made up of gases, so they are known as. And Jupiter has got 79 satellites of its own. Next slide, sir. So here, earlier we all knew that Saturn planet has rings. Even with a small telescope, the rings of Saturn can be seen. But Voyager spacecrafts have detected rings around Jupiter, Saturn, Uranus, and Neptune. So here, this is again a photograph taken by Voyager. You can see the rings. Saturn rings are made up of stones, but these are all gases. So though Jupiter is very nearer to us, Jupiter rings cannot be seen because the gases absorb the light, and the stones of Saturn, they reflect the light. And how small Sun looks from Jupiter in this image you can see. Next slide, sir. This is the most beautiful planet of our solar system, that is Saturn. Saturn is also, as I said, made up of gases, hydrogen and helium. Its density is less than 1. So if Saturn is kept in a beaker, big beaker containing water, then Saturn will float like a balloon. That is there. And then Saturn has got more number of satellites than Jupiter. Jupiter has 79, Saturn has 81 satellites. And this also got a beautiful ring structure. As I said, it can be seen through even a small telescope. And yes, Jupiter rotates 9 hours 55 minutes, and it takes 12 years to go around the Sun. So we have 12 zodiac constellations, and each year Jupiter will be in one zodiac, whereas Saturn takes 30 years to go around Sun. So 2.5 years Saturn remains in one constellation, zodiac constellation. And Saturn, next slide, sir. Yes, these are the rings of Saturn. We are seeing them in the equatorial plane. These rings are very, very thin. That is like a blade of razor or a paper, where the length will be very high, large, and thickness will be very less in microns. Here, this is the length of these rings is more than 3 kilometers, whereas width is less than 1 kilometer. So these are the Saturn rings. These rings were seen by Voyager spacecrafts and other Voyager spacecrafts. Next slide, sir. Yes, Saturn has got some big satellites of Saturn. Enceladus, Titania, all these. So this is Saturn, just a family of satellites around Saturn. Next slide. So here this is Titan, the satellite of Saturn, where methane, ammonia gases are present in this satellite. So it is said that after billions of years, when the sun expands and becomes a red giant, then the Earth won't be there at that time. The sun will expand so much that even Mars will be taken inside. But temperature, the heat that reaches Titan will be so high that the temperature of the Saturn will be sufficient. Titan will be sufficient for life to develop. So there is a possibility of life developing on Titan after, say, a billion years or so. Next slide. Next to Saturn is Uranus. Uranus is bluish in color. This blue color is due to the presence of methane and ammonia. And Uranus, as you can see, the rings are 90 degrees. They are going around 90 degrees. That is, the Uranus is inclined 90 degrees on its axis. That is why the rings are going perpendicular. In fact, all the satellites of Uranus, they will be going perpendicular to the orbit of Uranus, and Uranus will be also rolling around the sun. That is it. Next. These are some of the satellites of Uranus. Uranus has got 27 satellites. These are some of the big satellites: Ariel, Miranda, Titania, Umbriel, and Oberon. These names are taken from Shakespeare's play Tempest. Yes, sir. Now it has become big. Neptune. Neptune. Here the planet Neptune is Voyager has discovered in 1984 the rings around planet Neptune. So these rings, Neptune, Uranus, Jupiter, they are all made up of gases and dust particles. So here you can see the planet is totally covered and a long exposure is given, and you can see many rings around Neptune. So this is how the photograph is taken, by covering the main planet and then giving the exposure so that the faint objects are visible. Neptune has got total 14 satellites. Next slide. Next, sir. Yes. Now this is the definition of Pluto. What Pluto is: the celestial body that orbits the sun, and second also is same as the first one, what we have seen for planets, that is spherical hydrostatic equilibrium, but has not cleared the neighborhood and is not a satellite. So all these things make has declassified Pluto as a planet, and Pluto has got a very similar object of almost same size. In the next slide we see. Next slide. Chiron, you see almost the same size of that. So now Chiron is classified as a minor planet. And next, next is, beyond, now we have crossed Pluto, and in the solar system there are also comets. These comets, they come from a very big cloud known as Oort's cloud, which is around 50,000 astronomical units from the sun. And this cloud, when some star passes close to that, because of the gravity, some portion of the cloud, it gets separated and it starts coming around the sun. And when comet comes to around 5 astronomical units or so, then the dirty ice called cometes, and the ice melts and the tail develops. When it comes more closer, it gets 2 tails. One is the dust tail and another is gas tail or ionic tail or a plasma tail. Next slide. So here you can see this is how the comet it is going in its orbit. When it comes very close to the as it approaches the sun, slowly the ice starts melting and the tail develops, and as it again goes back, when it is going back, recedes, then the tail gets detached from the parent this comet, and it will remain there in the sky as debris. Sometimes we see them in the form of meteor showers. So the comet again goes back. Every time when it comes, it loses around 10% of the mass. Next slide. These are some of the ions that are present inside the comet. The comet has got nucleus and then a coma portion and then a halo. All this, so I can't see honestly. Screen is small, but a coma, you can see what are the ions present there in the comet, and this is one is the gas tail, another is dust tail, and then because of the this is here on the right side, what you see is the solar wind. Because of solar wind, the wind pushes the ice and then it becomes the tail. Yes, next slide, sir. Next slide, sir. Yes. Now this is sun. Sun has got 3-4 layers of sun. One is core, that is the totally inside, then radiative zone, and then outside is convective zone. In the core, the nuclear reactions take place. Hydrogen gets converted to helium. So because of that, this energy is generated. That energy reaches there earlier in the form of little in radiative, then again in convective zones, and then it reaches the surface. In fact, from core to surface of the sun, the energy takes millions of years to reach. From there, we all know that the light takes 8.3 minutes to reach from sun to earth, we say. But from core to surface itself, it takes millions of years. So the radius is only 7 lakh kilometers. So sun is a star, a huge star. The temperature is around 6,000 degrees, and when you compare to other stars, it is a very small star. Next slide, sir. Okay, here you can see the comparative sizes of the stars. So sun is very small. If you see a dot, earlier we have seen for solar system how big sun is and how small the planets are. In a very similar way, Betelgeuse, Antares, all these are very big stars when we compare it to Sun. There are many stars which are very much bigger than Sun, and this Sun is a very small star when we compare to these other planets, other stars. Next, sir. Okay, this is about the life story of a star. That means just like humans, the stars also live for certain time and then they die. So the stars evolve like humans. Initially, there is a nursery, and then the stars, the humans also from nursery, they start growing up, and then they reach, they become adults, and then after certain time, they evolve and they become old and die. In a very similar way, the stars also evolve. So how that is found is if we compare the this is done using spectroscopy, photometry, where luminosity of the stars is found, the temperature of the stars is found, and we find that there is a very good relation between luminosity and temperature, where most of the stars, which is known as main sequence, where the star remains for quite a lot of time, most of its life, like we all up to the age of say 60, 65, the peak period of our life. So that way the stars also have their peak period where it is stable, and then later on they become giants, supergiants, white dwarfs, and all that, where they go away from the main sequence. You can see in the giants what happens is the temperature remains almost same, but luminosity increases. Supergiants also same. If you see a white dwarf, the luminosity drops and temperatures are very high. So that way, this is known as a HR diagram, Hertzsprung-Russell diagram. So, which tells about the classification of stars is done in this way by comparing their temperature or mass with luminosity. Next slide, sir. So, this is again, as I said, Sun, then a giant star here. Now, when giant star becomes a small dot-like thing, supergiant. So, supergiants are very big when compared to Sun. Next slide. So here, as I am telling the evolution of stars, this is the main sequence. So the stars have different masses. Sun mass is a relative mass, which is known as one solar mass we call, and all the stars we take in the, let's say, 0.5 solar mass, 2 solar masses, 3 solar masses. So Sun has got say 10 billion years of life. The stars which have more mass, they live for less time, and the stars that have very less mass, they live for more time, 100 billion years. Then stars, A-type stars, O-type stars, or where the temperature is 30,000 degrees, 20,000 degrees, and 10,000 degrees. Sun is, as I said, 6,000 degrees is the surface temperature. So the above stars, the blue stars, hot stars, they live for short time, and then the yellow and red stars, they live for long time. So this is the evolution of stars, where you can see the duration also is given. Life is how much time. Next slide, sir. So as I said, we study about the stars by knowing by taking its spectrum. This is just a periodic table. Spectrum means how it looks. We all know periodic table, but when we compare each element's spectrum, you find that they are totally different. So when we try to take the spectrum of stars, we find all these lines in different wavelengths. So we find some lines in different wavelengths when we try to find out what stars, what elements are present in the stars. So by knowing the elements or the ionization levels of those elements, we can tell the temperatures of the stars. By one famous equation, Saha's equation of ionization, where the ionization levels and masses are related, with which we tell the temperature, all these. Yes. Next. So here we talk about the evolution of stars. So see, as I said, the low mass stars and high mass stars. In low mass stars, we have this carbon dioxide, carbon, oxygen. Initially, hydrogen gets converted to helium, and we have a helium shell. What happens is initially only hydrogen is there. Because of nuclear reactions, the temperatures, because of self-gravity, if you see the formation of star, initially only gas is there. That gas starts contracting, and when it is contracting, the density increases, the temperature increases. Then the temperatures increases because pressure increases. Because of that, the nuclear reactions start taking place. Hydrogen gets converted to helium. So when that occurs, the radiation comes out. So there is one force of gravity that is pulling the star inside, and then the outward radiation that is pushing the gas outside. These two become stable at certain time, and then we call that star is in the form of state of hydrostatic equilibrium. So at that time, the star is said to be on main sequence, where it continues for longer time. When again total hydrogen gets burned to helium, what happens? You get a helium core. Helium core, again the star becomes unstable. The gravity pushes helium inside, and because of that, the star bit expands, and then more elements and more reactions start taking place. So if you see that in the small star you have carbon oxygen core, then whereas in the, if a star is of very high mass, you can see the iron core inside. Okay, all these different layers like we have in the onion peel. So these kind of layers are formed, and finally when you have an iron core and no more, at that time no more reactions take place, the core starts contracting, and because of the heat that is released, the shell starts expanding, the star becomes very unstable and it explodes. So depending upon the mass of the star, it will become a giant or a supergiant, and then there will be a supernova explosion. Next slide. So this is how, see, the stars are formed. You have stellar nursery, and then sun-like star and more massive stars. So it becomes stable, and then planetary nebula. That means you have gas around the star is inside, and outside there is gas, but later on when it expands, depending upon the mass of the star, it will either become a white dwarf or a neutron star or a black hole. Next slide. Yeah, here you can see if the mass is less than 1.4 solar masses, it becomes white dwarf. If it is more than 1.4 and less than 3, it becomes a neutron star, and if it is more than 3 solar masses, it becomes a black hole. The electrons run out of room to move around. Electrons prevent further collapse. Protons and neutrons still free to move around. Gravity is more, but white dwarf is very less dense compared to neutron stars. In black holes, finally, everything will be collapsing, and there is no outward pressure, so everything will be collapsing. And in black holes, the speed of collapse is more than the speed of light, so even the light cannot escape from the black hole. Next slide, sir. Then we go beyond the stars. This is a Nachieketa or Pleiades cluster where the stars are being formed. These are known as young stars, hot O-type stars, B-type stars, where the temperatures are very high. As I said, if temperatures are high, their life is less, age is less. So these are formation regions of stars. Nachieketa cluster, which you can see easily Pleiades in the Taurus constellation. Next slide, sir. So now I am showing you what are the things available in the universe. This is one nebula in Orion constellation known as Horsehead Nebula. Of course, the picture is taken. You can see a head in the form of horse. So this picture is taken in infrared. Maybe James Webb Telescope will take a better picture than this. So this is this nebula is in Orion constellation. Yes. Next, sir. Yes, yes. That here you can see protostars again in the Orion Nebula. Hubble Space Telescope has seen there are many stars and gas around it, which means that the formation of stars or even the planets, some oblate portions can be seen, which says that planets around the stars are being formed. Next slide. So these are known as pillars of creation in Eagle Nebula. So Eagle Nebula is also M16. Hubble Space Telescope has seen this. This doesn't look like Eagle, but with normal telescope, the entire portion appears like Eagle. This is a very close-up view of that nebula. These are known as pillars of creation, where star formation is taking place. Yes, next. Next slide is very interesting one. See, the left image is taken by the Hubble Space Telescope and the right image with the recent one, JWST, James Webb Space Telescope. This JWST focuses more on infrared region and Hubble is in optical region. So a lot of stars are covered when the photographs were taken by Hubble Space Telescope, whereas here you can see even the stars. Normally, if the dust is there, the light that is coming out from the stars is in the infrared radiation. So these things are could be captured through James Webb Telescope. So this picture is of James Webb. Here everything is covered. This is of the Hubble Space Telescope. Next slide, sir. So if we cross beyond this nebula, this is one globular cluster in which there are thousands of stars, and we are moving further and further. So thousands of 10 to the power, not thousand, 10 to around millions of stars, 10 to the power 6 stars are there. So this is a globular cluster with heavy stars. These are known as some old type stars. That is, the temperatures of these stars are less. And yes, these kind of clusters can be seen. Next is Andromeda Galaxy. This Andromeda Galaxy is 2.5 billion light years away from us. So this is the nearest galaxy to us. So this can be seen even through a small telescope. And even if the sky is very, very clear, then with naked eye, we can see Andromeda Galaxy. This is the nearest galaxy to us, and it has got 2 satellite galaxies also. Next picture. Yes, these are the spiral galaxies. This one, the next one, the above next one. These are all the spiral galaxies. You can see how tight the spiral arms are bound. In this way, the classification is given S, A, S, B, S, C. These are all spiral galaxies. Yes, the one where arrow is, you can see the galaxy. In fact, it will be like this. When we are seeing a galaxy face on, it appears like this. If you tilt it, it is not necessary that all the galaxies will be facing us. But if it is little tilted, they will be elliptical in shape and all that. The shapes of the galaxies also vary. So this is a very face-on galaxy. Next, sir. So here we can see how big the universe is and what is our place in the universe. So you can a solar system where there is a galaxy. In a galaxy, there are around 10 to the power 11 stars in Milky Way galaxy, our galaxy, and in that, Sun is just a very small star, a small G-type known as with the temperature of around 6,000 degrees, 5,800 degrees, and like Sun, there are 10 to the power 11 stars to Sun. There is solar system. There are 8 planets in solar system, and the third planet, Earth, has life. Other planets do not have life, and so it says the position of Earth and humans or our place in the solar system. Yes, in the galaxy. Next slide, sir. So this is another galaxy. The galaxies also collide. This picture is now known as a cartwheel galaxy because it appears like a hula cartwheel where two galaxies have collided and collisions of galaxies take place and collided, and this kind of galaxy is formed where you see the bright portions are in the edges and also in the central portion. So we really do not know how this galaxy is in equilibrium state, because in between there is lot of gas and then in the edges there are again many massive stars. Next slide. Yes, this is Edwin Hubble. Hubble is the first who looked at the galaxies, and he said that till Hubble, just like till Copernicus, it was thought that Earth is in the center and all the planets go around the Earth in a very similar way. Till Hubble has said that our Sun is part of a galaxy known as Milky Way galaxy, and there are thousands of galaxies at that time, thousands of galaxies which are not part of our galaxy, and they are all receding from us. Next slide, where he said that velocity of recession is directly proportional to the distance. Next slide, sir. So he has said that this is a very famous Hubble's equation where this velocity is proportional to distance, velocity of recession. And then he has also classified the galaxies E0, E1, E2 based on its ellipticity. E0 is circle, and then E1 elliptical, more elliptical, and then we again have spirals. In spirals we have SB, SB, that is barred spirals, where in between there are bars present. So all these classifications, they are done by Hubble. Yes, next slide, sir. Yes, see, this picture is taken, the deep field picture taken by